Okay. So I started out saying we have, if we follow the general recipe, then we can take two approaches to using these probabilistic methods. One was to find analytical expressions. Well, that was the topic up until now. And the other one is to let the computer basically handle this for us, and that is the topic of Monte Carlo simulations. The idea is more or less the same. You now generate in the computer as many random paths as you can, and if you do enough paths, then you will just assume that you have calculated actually any possible path. So you can just then add the probabilities of these randomly generated paths as a measure of what will eventually be the system. So instead of doing the integrations as we did before, you just simulate these paths often enough and assume that it will work. Of course, we already talked a little bit about Monte Carlo simulations earlier on. I want to briefly recap the method, how you actually sample in the Monte Carlo simulation, and then after that go to some applications of that. So the idea is we want to sample random quantities, for example, a path length without interaction or a scattering angle. That follows a distribution that we know. We calculated this Beer-type law of distribution for the path length. We know phase functions as distributions for scattering angle. So we want random values for these step sizes, for these angles, in order to build up a random photon path. The only problem is that the computer does not easily do that, of course. It generates uniformly distributed random numbers between 0 and 1. So what we have to do is somehow convert these uniform random numbers into random numbers that follow the distribution that we would like to see. So as an example, let's say that that a random variable is the sum of the eyes of the number of eyes if you throw 2 dice. In that case, there are 11 possible outcomes for the values. So minimum is 2, maximum is 12, and some of them can be obtained in multiple ways. So there actually are 36 possibilities. They are all equally likely. If you write the probability density function of this variable theta, then it would look like this, and I normalized it as well. So if we would add all these values up, it would be neatly evaluate to unity. So now the question is, how can we now generate random values of this variable theta using a uniform random number from the computer in such a way that that in the end this will it will follow this probability density. So the recipe for the computer would then be to draw such a random number first, then do some kind of transformation to convert that random number into a value of theta. We would store that theta in memory and repeat this process until we have a specified number of values of theta. And then we would calculate the histogram of all these random thetas, and that should then that histogram should then be equal to this required probability density function. Now the way to do that is first to inspect the probabilities of given outcomes. So there is only one way of throwing a sum of 2. That the sum equals 2. So the probability of that happening is 1/36. On the other hand, there are 2 possibilities to arrive at a sum that is equal to 3. So that probability is 2/36, etc., etc., etc. So we can calculate the probability for each of the possible outcomes. So what we could do then is draw this random number from the computer, uniform random number, and just walk along this set of rules. If it is less than 1/36, we would assign a theta value of 2. If it is between 1/36 and 3/36, so that the total range is 2/36, then we could assign a value theta of 3, etc. So for etc. for the next number of possibilities. So what we've actually been doing then in that case is that we have been looking to that uniformly drawn random number and actually see in which segment of the histogram it ends up, it falls, and then we assign that random number. So how does that work? So this is, of course, for a discrete probability density function with not that many possible outcomes. So the question is, how does it look if we generalize it to a continuous probability distribution? Then the problem is as follows: we have here on the right-hand side a given probability density that we want to sample from. So this is then the density P of X with values that can occur between 0 and between A and B, some minimum and some maximum. If you would integrate this over the domain, it would be 1. True probability density function. And what we have available is this from the computer. We get uniform random numbers somewhere between 0 and 1, all with equal probability. The trick is not to inspect the probability density functions, but to inspect the cumulative distribution function. So just as we laid all the elements here on a line and looked and put a uniform random number along that and see where the overlap was, we can do that here too. So we can calculate the cumulative distribution functions for both the uniform random number and for the quantity that we're interested in. So what you see here on the left-hand side is the cumulative distribution function of a random number, and that interestingly is equal to the random number itself. It is just a straight line, and we can calculate that. Or at least we assume we can calculate that as well for the variable that we're interested in. And now the trick in Monte Carlo sampling is to equate the cumulative distribution functions at some value. So the process is then as follows: you draw a random number, a uniform random number. Of course, then you would project that to the cumulative distribution function, which would give you the same number because that happens to be the same. But that uniform random number you then equate to the cumulative distribution function of x. So that gives you an equation, and then you can invert that equation to solve for a random value of x. That is basically this line going down here to the original x-axis again. So these are then the steps. You calculate the probability, cumulative probability functions for the random number that is just equal to the random number. For the function that you're interested in, you have to calculate it. You equate these two, and then you invert the equation that you obtain to solve for x. Now you can do that for step sizes. You can do that for angles. You can do that for absorption, or for all the processes that can occur in a photon path. You just need to identify the probability density function, from that calculate the cumulative distribution function, and then go through this process again and again and again. And that allows you to build up photon paths. You repeat that simply until photon is detected. Not sure why that is here. So how that works in practice, if you look at the internals of such a simulation, then usually the geometries are pretty simple. So again, assuming something that is layered, for example, but then with square or at least symmetrical layers in some coordinate system. So let's say take a Cartesian coordinate system, then the photons are launched into the tissue along the z-axis, and then they are tracked through this geometry until they either escape or are absorbed. So what you have to do is keep track of the position and the direction of these photons. So the position would then just be an XYZ factor, and the direction is usually stored with respect to the z-axis. So you calculate what is then called the directional cosines. So the cosine of the angles with the current photon trajectory with respect to the z-axis. So that are then these expressions that you see here. So the general procedure is then as follows. So you launch a photon, which means that you bring it into the tissue at x, y, and z is 0, for example. You calculate a step size, sample a step size in which no interaction occurs. After that, you calculate a deflection angle, so to determine the new direction of the photon. At this point, or maybe even before you calculate angles, you could decide whether or not the photon is absorbed or scattered. Then you propagate it again, you update its position, you update its angles, check if that is something that I'll get back to in a moment. But let's assume it is not absorbed or not detected, so then it is still in the tissue. So then you go back in the loop to the point where you calculate a new step size and a new set of angles, etc. You keep doing that until either the photon is absorbed or it actually reaches one of your detection criteria. For example, it escapes from the tissue again, and then you store the data, its data, and just start a new one. And you do that until you have simulated, let's say, 1 million or 10 million photon trajectories, and in that case, you say, okay, now I think I have enough stability in the data to stop the simulation and look at the results. So chapter 5 of the book is actually all about these Monte Carlo simulations. So a lot of the information in there is very readable. So there's not that much point in reading it out loud. I'll just point you to this one. It describes various geometries, for example, for starting a photon, for launching a photon. That can be, let's say, an isotropic point source inside the medium. So then you define a location that just emits photons isotropically in all kinds of directions. It could also be a very narrow beam that is incident on the tissue. So then all photons would, for example, start along the z-axis. But you can also make it more realistic. You can define a laser beam with a Gaussian intensity profile, so that more photons are launched in the center of the beam compared to the side of the beam, and that's actually the great part of these Monte Carlo simulations. You can add a lot of versatility as long as you can identify how to sample it. You can add a lot of complexity that you hardly can do in analytical modeling. So it is very powerful. So now let's look at an example of this. So let's see if we can sample the photon step size. So the size, the step a photon takes without interaction. So we knew already for the probability density for interaction-free paths that was given by this Beer type law. So mu s or mu t it says here, times exponential minus mu t times L. So now my question is, can you now go through the following steps? So calculate the cumulative distribution function from this one, equate it to a random number, and then solve L in terms of that random number, because that is how we sample it. Can you try that? Okay, so the first so the first step that we need to do is calculate the cumulative distribution function from this given probability density function. So the cumulative distribution function calculates in this case here calculates the probability of a path length between 0 up to some value of L. So the integration boundaries in this integral indeed are from 0 to L, and then maybe replace here in the integral replace the variable with the variable with the dummy variable. Yeah, so let's put it here. So in this case, that would be the cumulative distribution function P of L is the integral of the probability density function from 0 to L, and I've used L prime here now as an integration variable. So if you evaluate that from zero to L, then the answer is 1 minus exponential minus mu t times L. Accord?
Yeah, so far so good. But okay. Then the next step is.
Yeah, the next step is equating this to a random number. So basically, our random variable here is L, right? That is the random variable that we're interested in. And what we're going to do now is we equate this to a random, to a uniform random number that is drawn by the computer, and then solve for L in terms of that random number. That's the idea. So I'm not sure if the answer is going to pop up immediately, but yeah, it is. Now, okay. So we're going to equate this part to a random number, so that then gives us this equation, and then we can solve, and then we need to invert that. We need to solve that to get a random to L. So in this case, -1 to the other side. Take the natural logarithm and divide by minus mu t gives us this expression. And this is a little bit of a trick, because if the random number is between 0 and 1, then 1 minus the random number will also be between 0 and 1. So this is just that this just makes the computation a little bit more effectively. But what we have here now is we draw a uniformly distributed random number in a computer, RND, and through this transformation, that transforms into a random value of the path length that we can use in the simulation to put a step size, to make a step size. Is it clear what's happening here?
Yeah, though I had a bit of a difficult time relating the random number to a probability, which I think it is in this case.
Yeah, so the trick with the uniform random number is that it's if you calculate the cumulative distribution function of a uniform random number, it is just a straight line. So so that step, in effect, you don't have to do. You just draw the random number, and that is that's equal to its cumulative distribution value. Basically, okay. So the probability of drawing a random number between 0 and 0.75 is 0.75 because of the uniformness. Yeah, so then so that would allow you to take a step. There's a couple of ways in which absorption can be incorporated in such a simulation. This is only one of the ways in which each photon is assigned an initial weight of 1, and at every step that weight is reduced with a small fraction. If the absorption coefficient is high, then the fraction is higher. If the absorption coefficient is low, then that fraction is lower. But I'll just point you to this book, to the section in the book where it is discussed. Yeah, there is one. Okay, this I should mention. There is some benefit in not using absorption in the simulation at all, because if you remember, we started out with absorption that just happened along the photon path. So that means that if you do a simulation and you store the length of the path, then you can always add absorption later numerically. So you can just choose one simulation without absorption, and then in the end, you can just add absorption to the results to simulate different situations with absorption. The only drawback is that your simulation can run infinitely long, because if there is no mechanism of losing a photon, then it could be bouncing back and forth in the simulation forever. So you have to take care of that in some way. Okay, but this is that's all a little bit too much detail, I think. The other interesting thing to sample is the scattering angles, so the phase function. So we know from the definition of the phase function that it is normalized on the solid angle domain. That's this equation over here. But what we now want to do is sample the scattering angles theta and phi, and not some combination of it. So we first have to split this joint probability distribution for the angles into the two marginal distributions, for angle theta and for angle phi. Now we also knew that most phase functions do not have an explicit dependence on phi, so we can actually go through this quite quickly. We can to obtain the marginal distribution, we have to integrate over the other variables, so we can do that for theta. When there is no functional dependence, then the result will simply be that PDF of phi is 1 over 2 pi, and that also will mean that whatever the expression for p of theta phi is, if there is no phi dependence, then the isolated marginal distribution for p theta will be the same factor 2 pi times the original way of writing it. So, for example, let's take the Rayleigh phase function. The formal definition, where it is normalized over solid angle, is given by p of theta and phi is 3 over 16 times pi, and then the cosine term. But now for the Monte Carlo simulation, we want to have two separate equations. We want to draw two random numbers, one to sample phi and one to sample theta. And actually, it is even more convenient is not to try to sample theta, but to try to sample cosine theta, because then this equation just becomes a polynomial expression. So step one would be for this in this approach would be to find the marginal distributions. Can you give them quickly to me? So the distributions for theta and the distributions for phi and the distributions for cosine theta. Remember that rule of thumb that there is no dependence on phi in the phase function. No functional dependence.
So was the marginal distribution the 1 over 2 pi for?
Yeah, that was the one for phi.
Okay,
it was just 1 over 2 pi, and then for the marginal distribution for theta.
Yeah, that was 3 over 8, 1 plus cosine squared theta.
Yeah, exactly. Then you can just multiply this expression here with 2 pi, and then yeah, and then that results. So the marginal distributions here for phi is for phi is given here 1 over 2 pi. For theta, it will then become 3 over 8 times 1 plus cosine squared theta. And if you write this as a function of x is cosine theta, then this is the result. Okay, so the second step would be for both of these functions to find the cumulative distribution function. Any thoughts?
Yeah, we have to do an integral again over some interval, right? And the integral is over the argument of the function.
Yeah. Yeah. So in case of just skip to the next slide. So for the case of phi, the PDF was 1 over 2 pi here. To calculate the cumulative distribution function, that is then this line. It's a little bit of a messy slide. I'm sorry for that. It's then the integral from 0 to some value of phi of that function, day phi prime. Of course, this is just a constant, so that integral is not that complicated, and it becomes phi over 2 pi. For the cosine of theta, for the parameter x, it's a little bit more work. So this was the probability density function. So theta runs from 0 to pi is the domain. That means that x, cosine theta, runs from -1 to 1. So if we want to calculate the cumulative distribution function for x, we integrate from -1 to some value x over there. So in that of this expression, 3 over 8 times 1 plus x squared. So it's an x. And this is also an x. I'm sorry. So then in the end, that's just a polynomial expression. So we end up with this final result. So the cumulative distribution function for x is given by this expression. Okay, now for both of these, we have to equate them to a random number, to a uniformly drawn random number, and then solve for phi and for x. So what is that going to be for phi?
So for phi, it would be 2 pi times the random number, right?
Yeah, exactly. That's the easy one. That is just going, and that gives you just a uniformly distributed phi.
Mm-hmm.
As you would, okay. And for x,
yeah, that one is a lot more messy.
that's terrible, huh? It's it becomes a third order equation, and that is not so straightforward to solve. So what we run into here now is that the procedure is clear, but for almost the simplest phase function that we can find, it already becomes complicated to do the sampling. And so this would be this is what we would get. So for phi, it is 2 pi times the random number. That is not so difficult. Inverting this equation is much more difficult. It can be done. It's called Cardano's formula. That is just like there is for a quadratic equation, there is also a recipe for solving a cubic equation. Then the result would be this. So first we calculate an intermediate parameter u. Spoil things. An intermediate parameter u here that depends on the uniformly drawn random number, and then there is some additional calculation with a lot of cube roots and roots that transforms these values of u into a value of x, of cosine theta, and then if you really want to have theta itself, then you can still take the arc cosine, the inverse cosine. So it can be done. But most Monte Carlo implementations do not do this because, well, one reason is that it's computationally not that efficient, because calculating these roots takes relatively a long time. So if you want to at every scattering event sample new angles, then the simulation would take a long time. So what most codes do is they use the following approximation. So instead of the full 3 over 8 times x plus x squared of x to the third over 3 plus a half, they use this approximation. So this is approximated by a half times x plus 1, and if you do that, then it's easily invertible, of course. Then x of cosine theta becomes 2 times the random number minus 1. And if you then look at if you would look at the graph with x and the random number on the axis, then you see that it does not make a huge mistake, or so it seems. I just want to show you. I have to share another screen for that. So 1 second. This one. Yeah. This is a calculation of that Rayleigh phase function. I'm going to click a few out here. So this is the actual phase function, the actual Rayleigh phase function. So on the horizontal axis we have the scattering angle in radians, and on the vertical axis here is actually the ground truth. So the idea is now to draw uniform random numbers, and then do that well, in this case 100,000 times, and then calculate the histogram, and that should equal this this input true phase function. This is what happens if you make the approximation. Even though in the slide it appeared that the error was not so big, as you can see, this is a totally different form of the phase function. So this is actually not such a good idea. There was another option that we discussed earlier on, that was based on drawing two random numbers. You could draw a random number somewhere on the horizontal axis here, and draw a second random number on the vertical axis over there. If that point that would follow is below the curve, then you would accept the random value on the horizontal axis, and if it is above it, you would reject it, which means that basically that you have to draw more random numbers to calculate the values of theta. So this is an example for that simulation. So again, 100,000. Now you see that at least the histogram of the drawn thetas nicely overlaps with the true phase function. So that's good. I also calculated here what the ratio is of accepted points over rejected points. So that means that it is not very efficient. Only 75% of the points are actually accepted. So that adds to the overhead of the calculation. Of course, we can use this Cardano's formula to sample. That also gives a good result. That also matches the input curve very well. And then you can do some other tricks, but I'm not going to elaborate on that too much. Some other tricks where you split the phase function into two parts, which you sample individually, and that would also give you a good result. So the point is that there are ways around it. Funnily enough, most Monte Carlo programs that you find online still use this, but there are options to actually do it in the correct way. All right, then I go back to the presentation. Hopefully. Okay, so then once you have these angles, the theta and phi sampled, then you're ready to deflect the photon. So that means that you have to update its direction, which means that you have to update these directional cosines with respect to the z-axis. Now that's, as you can see, that is a nice exercise in geometry, but you can calculate that this is the way the new direction relates to the old direction here on this side, and the sampled scattering angles. So that is doable. Then if you have the angles, you know the new direction and you know the step size. That means that you can update the coordinates of the photon, where it is in the medium, and based on that you can check whether or not it has escaped or not, for example. So that's that. So this is then again the flow chart for propagating a photon through the medium. Okay. At some point, so if you, let's say you're simulating a medium that is infinitely deep and infinitely wide, at some point a photon may be somewhere far, far away with very little probability of actually escaping back to the surface again. So that would mean that you are simulating a photon, or tracking a photon that will never contribute to your signal. So there is a few tricks for that. Usually they come by some name like a Russian roulette, where you just again, based on a random number, decide whether or not you are going to continue with that photon or if you're going to terminate it. So if you assign a weight to each of these photons, then at every interaction step, a little bit of that weight is lost to account for absorption. And for example, you can say if that weight falls below a certain threshold, I'm going to draw a random number. If that random number itself reaches a certain threshold, I'll keep the photon. If not, I'll terminate it, or the other way around, depending on your definition. Of course, you can make this geometry as complicated as you like. You can make boundaries. You can define layers with different optical properties, or you can define inclusions in these properties. Any way you like. It also means that you have to be careful that when a photon crosses one such boundary, that you're careful to, for example, update its position appropriately, or update its angle appropriately. For example, when you have a refractive index mismatch, then due to Snell's law, there will be some change in direction, and you have to account for it. So you can make it as complicated as you like, basically. Then, if the photon escapes from the medium, then there are again a few options. You can define a grid on the surface and keep track where the photon actually escapes. So that means that you can simulate spatially resolved reflectance, for example. You could also define some collection optics in the computer, for example, a fiber with a certain numerical aperture. So when the photon escapes, you check whether its angle is within this numerical aperture. If it is, then you count it. If not, then it is discarded, etc., etc. So you can make this quite complicated. Okay, one final demo. To go back to another slide again. So this is how such a simulation could look like. So this block here, what you see here in 3D is a medium which has certain dimensions in the x and y direction that is on the surface, and then the z direction is into the medium. It's a little bit strange. So in this simulation, in this particular simulations, the photons enter from below at x, y, and z is 0 and are shot into the medium. I'll just going to start running it, and you can see. So this specific medium is defined with a scattering coefficient of 5 per millimeter and an isotropy factor of 0.9, which means that most of the scattering will occur in the forward direction. And in this case, the photons are traced until they are reflected again. So they escape the medium from the XY plane. And the weird things that you see going here now are individual photon paths. So these are calculated by calculating a step size, calculating deflection angles, or sampling deflection angles, I should say, then a new step size, then a new deflection angle, etc., until they are detected. And as you can see, the variety in possible paths is really enormous. Sometimes it is short, sometimes they are long, sometimes they appear to take forever. Sometimes they go deep, sometimes they stay near the surface. So this large variation actually tells you that you have to do you have to simulate a lot of these paths to build up something that would resemble your actual measurement. So in your actual measurement, all these paths would also occur. So you have to sample enough of them in order to find the path. So here on the right-hand side, for example, you see a histogram of the step sizes in this simulation. well, that was supposed to follow Beer's law. So if you plot that on a logarithmic vertical scale, then it will become a straight line. So that nicely works. This is an histogram of the deflection angles theta that are in the simulation. As you can see, these are all pretty small angles, which corresponds to a high value of the anisotropy factor. So if I stop the simulation and set the G value to 0, for example, so isotropic scattering, then what I will expect to see is that the distribution of scattering angles will become broader. Or actually, it will become uniform because I set G to 0. You see that happening as well. So basically, this is then the way in which the simulation is built up. We can derive all kinds of statistics from such a simulation. We can, for example, keep track of the path length of the detected photons. So this graph here on the top left shows the log of the path length. So that is on the horizontal scale, and here the count, the number of photons that actually arrive with that path length. You can make an histogram of the escape angle, so the angle with which the photon escapes the tissue, and for example, compare that to the Na of a fiber. You can check how far from the injection point the photons actually escape. So this is a histogram of count on the vertical scale versus position from the entrance point. So you see from here that most of the photons actually escape very close to the location that they were launched in, etc., etc. So you can do a lot of statistics. All right. One final jump back to the slide, because it is also time, I see. This was the final demo. What I would like you to read on this topic is chapter 5. That is already on the Canvas, I think. What we're only concerned in this presentation, but also for the book in the steady state modeling. So you could also add a time component even to this Monte Carlo simulations, but that's a little bit too much. So we're only looking at a steady state. And I'll also put a short document on there that basically just summarizes all these approaches. So that is what I would like you to read. And then I have one final question, and that is about this course. There is a short evaluation form with a few questions that is on this link. I'll try to put the link in the chat as well. My question is, could you please take a moment now to fill it in? It will only take you a few minutes, but then I'm sure that I have enough response to pass through. That would be very much appreciated.
Can it also be later, because I already had plans now?
If you promise you'll do it, and then of course.
I have a question about reading. I saw some other chapters on the Canvas page as well.
Yeah.
Could you maybe make an announcement about which parts are interesting to read for
definitely.
the modeling?
Yeah.
Or the oral exam, I mean.
Yeah. So I'll make the announcement. I'll do the announcement ASAP. And but my plan was to discuss all this on Friday as well.
Okay.
So Friday we have the last class. I'm not going to talk about new subjects anymore. So I just want to give an overview of what we have been doing and try to knit it all together and put it in the right order. So, but I'll do the announcement as well.
Okay, then see you Friday, I guess.
Okay, bye.
Bye.
Can I also ask concerning the exam, are we definitely settled on Thursday?
I think so, yeah.
Okay, lovely. Thank you.
Yep.
Bye.
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 Bye. I filled it in.
Okay, dankjewel. And that wraps it up.